Okay guys, next we have Larsmas precision and Larsmas theorem. First I will define it and then we can move towards the proof of Larsmas theorem. It tells us that when an atom is placed in an external magnetic field, B, the electron orbits precesses about the field direction similar to the precision of mechanical torque in the gravitational field. This is called Larsmas precision. What it means? Suppose we have an electron which is moving in this elliptical orbit, and the angular momentum is perpendicular to the plane of this orbit. Suppose this is the electron motion. Now if we apply an external magnetic field in the z direction, then this orbital angular momentum presses around this external magnetic field. So this is the precision of orbital angular momentum around this magnetic field. So it moves like this. This precision is called Larsmas precision. And according to Larsmas theorem, the frequency of precision which I represent by this letter nu rail of electron orbit about the field direction is given by nu L is equal to EB over 4 pi m, where E is the charge of the electron, B is the external magnetic field, and m is the mass of electron. So this is Larsmas theorem, and this is Larsmas precision definition. So here we will prove this formula now. Now we will move towards the proof of this formula. For that I will move to the above diagram again. Consider an electron which is moving in elliptical orbit. Suppose this is the motion of electron in elliptical orbit. We can say the electron is moving in this orbit, and this is the direction of motion of electron. Now suppose we apply an external magnetic field which is perpendicular or which is along the z direction. Now the angular momentum of this orbit, the orbital angular momentum direction will be perpendicular to the plane of this orbit. I call it L. Now this orbital angular momentum vector precedes about this external magnetic field like this. In this way. So here we have this L. After some time it moves to this point. So here we have again the L vector. It comes to this point. So it's precedes around this external magnetic field like this. Now electron is moving in this circular loop, and the motion of electron around the nucleus is equivalent to a current loop, and the current produced due to the motion of electron in this loop is I, which is equal to charge per unit time. Now the charge on electron is E divided by time. I taken it to be time period of oscillation, where T is the time period and it is the time taken to complete one complete revolution. So let's suppose an electron start moving from this point. Once it complete a complete rotation again come to this point, then the time taken is called time period. Let's say this is equation number 1. Now time period or time can be defined from the formula. We know the velocity is equal to distance covered per unit time. Time is equal to distance per unit velocity. So we can define the time period T, which is equal to distance covered in one complete revolution. Distance covered in one revolution divided by speed of electron in the orbit. In the orbit. So this is, we consider it to be a circular loop, and we know that the circumference of a circle is, so it covers the whole circumference. So the circumference of the circle is 2 pi r if its radius is r divided by the speed v. This is equation number 2. Now using equation 2 and 1, we have the current I, which is equal to E over 2 pi r over v. So it's equal to EV over 2 pi r. This is, let's say, equation number 3. Now this is the current generated by the motion of electron in the orbit. Since electron is moving in anticlockwise way, electrons are moving in anticlockwise way, so the direction of conventional current is clockwise. This is the moment of electron, and the direction of current is clockwise. Now the upper phase of the loop become south pole, and the lower phase become north pole. Due to this, a magnetic dipole is formed, and we know that magnetic moment is associated with magnetic dipole. Thus the orbital angular momentum or the orbital magnetic moment is, since north and south pole are created here, so due to this a magnetic dipole moment is formed, and we know that magnetic moment is also associated with magnetic dipole. Thus the orbital magnetic moment, which we represent normally by this mu symbol, mu L. L is for the orbital. So mu L is equal to the current flowing through the loop times the area of the loop. Now current formula is given here in equation 3. So using equation 3 we have EV over 2 pi r into area. Area of the circular loop is equal to pi r square. This is area of circular loop. Though we are discussing the elliptical orbit, but for the calculation I am using the special case, which is a circular orbit, and the area of a circular orbit is pi r square. So pi cancel with pi, r cancel with this square, so we have the magnetic moment mu L, which is equal to EV r over 2. Let's say this is equation number 4. Now multiply and divide equation 4 by multiply and divide equation 4 by mass of electron. The right hand side of this equation 4 by mass of electron, we have the magnetic moment mu L, which is equal to E times mvr divided by 2m. And we know that the angular momentum, which is equal to mvr from Bohr theory. So if I use this value here, we have the mu L value, which is equal to EL divided by 2m. We can write the magnetic moment divided by angular momentum is equal to E divided by 2m. Let's say this is equation number 5. Now when an atom is placed in magnetic field, then torque experienced by the magnetic dipole is. So the torque experienced by the dipole moment is tau, which is equal to mu L B sine of theta. Because we have a dipole moment, as we discussed in the dipole moment of electric charge, that when a dipole is placed in external electric field, then this dipole moment ally itself, or this dipole ally itself in the direction of magnetic field. So how it can ally itself? It will rotate. So this will come in this way, and this will go in this way. So there is a torque produced in this dipole moment. Similarly, when a magnetic dipole moment is placed in external magnetic field, then again that dipole moment ally itself in the direction of magnetic field. So torque is also produced in that dipole moment, which is given by this relation. While in the case of electric field, we have the torque, which is equal to P E sine theta, where P is the dipole moment, which is equal to QD, and E is the electric field, or we can say that tau is equal to P cross. So this is the same situation is for the magnetic dipole moment. So I will stop my calculation here, and then I will do the rest of the calculation in the next video.